Good day, I am Adriel Elamparo, presenter 27, a student from Maputo University, Philippines. And today I'm going to present our study paper ID 17 entitled Rust Detection on Galvanized Iron Sheets using Convolutional Neural Network and Mass RCNN. Introduction. Infrastructure care is done to preserve stability, order, and safety to prevent unwanted deterioration and hazards. One of the materials that are prone to deterioration are metal sheet roofs. Metal sheet roofs protect from environmental factors such as intense heat and rain. Due to this, it is also the most vulnerable to corrosion, particularly rusting. And a prominent material are galvanized iron sheets. However, even with this, rusting still occurs and requires regular monitoring. Smart methods have emerged with advancement of technology, and this paper presents convolutional neural network or CNN and mass region-based convolutional neural network or mass RCNN in classifying and locating rust on GI sheets. So now we want to emphasize that we have conducted our study through machine learning and computer vision means. Our study is divided into two parts. One is for classification and one for detection. But what is the difference between the two? In layman's term, image classification predicts what kind of image the sample image is from a set of data. In our case, a rust image may be classified to no rust, slightly visible rust, or heavy visible rust. On the other hand, object detection predicts where the object is within the image. In our case, the rust locations within a classified image are detected. In doing this paper, we have reviewed these related studies that have helped us in developing our study. A study by Wang and Co. In their methodology, they have used a software that transforms images into grayscale, then segments the damper from the background, which outputs two parameters. These parameters are used as indicators in identifying rust status. Second study by Diaz utilized RGB channels in detecting rust through thresholding, edge, and segmentation. Third study by Ivanesco and Co. used the HSV color model in segmentation rather than the RGB color model, and concluded that the saturation component is the most relevant in HSV for segmenting rust as it can be identified in the image. Fourth study suggested that the HSV model could be enhanced by utilizing a fully convolutional neural network unit. Fifth study delved into detecting pitting corrosion, and sixth study wherein rust classification categories were identified and used by researchers as basis for classification. And lastly, a study by Yumang employed that the use of mass RCNN can be used in detection. With the review of the related studies, our group noticed that there is a need and there is a gap in the detection of rust. Smart methods have been used and developed with computer technology, and many image processing methods have been developed for rust detection. But this study focuses on how computer vision with machine learning can be used to detect rust. But rust in itself has no definite shape and is not a distinct object, unlike other objects for computer vision detection. Due to this, it is important to identify and develop a rust detection system that can classify and locate rust through computer vision with good performance. In line with this, our specific objectives are to classify rust image as no rust, slightly visible rust, and heavy visible rust using CNN. Second, to locate rust in images of GI sheets using mass RCNN. And third, to test the prototype's rust classification and localization under different lighting environments. The limitation of the study is that the problem is treated as a computer vision problem. This means that the classification and localization of rust is based on what the system sees in a frame. Rust that are underneath the sheets were not included, but rather rust that are visible and present on the surface of the sheet. And only rust on galvanized iron sheets were considered. The models used for classification and localization had incompatibility issues when used together. However, a linking method with an external Raspberry Pi bypassed the limitations. Now to give an overview of the models used, and the first is CNN. CNN is a class of neural network that specializes in processing data that has a grid-like topology, such as an image. A digital image is a binary representation of visual data. It contains a series of pixels arranged in a grid-like fashion that contains pixel values to denote how bright and what color each pixel should be. The efficient B7 pre-trained model is utilized for this study. In this, each image is entered into the network's input layer as an array of values based on the color of each pixel. The convolutional layer of the model receives the arrays scanned using several filters. The characteristics of an image are the outputs of this layer, and the output layer, the network's last layer, uses them to predict the classification of the image. Next is mass RCNN, and it uses the object mass pre-labeled on pictures before training to find and locate objects in an image. The picture is subjected to filters, much like CNN, to create feature maps that produce data that fits the object mask. The Tectron 2 with mass RCN and R50 FTN TX model was utilized in the study. The model is trained using a dataset that includes rust containing photos or images previously annotated using an object mask. The object mask aids the model in learning which features help in recognition of rust in an image. Using the same object mask that was used to detect them, the model can visually indicate any rust regions or spots it finds. So here are the models used: efficient B7 model for CNN, and the Tectron 2 with mass RCNN R50 FPN3X model for mass RCNN. So for our dataset, a manually acquired rusted governance iron sheet dataset was used since no existing rust dataset is available. 344, 84, and 40 images were allocated for training, validating, and testing respectively. The training dataset was used for CNN, mass RCNN, and these images were then sorted into the RAS classification categories. So for rust classification categories, which are no rust, slightly visible rust, and a heavy visible rust, were used in categorizing the rust images captured from galvanized iron sheets and was treated as the classes for the rust classification. And an expert verified the sorted images in the custom dataset and was used in the study. And here is our conceptual framework: input raw images of GI sheets with rust, process annotation, and the training for CNN and master CNN. And the expected output is a prototype that can classify and locate rust on galvanized iron sheets. So in our process, we have annotated and drew bounding boxes or polygons to the target object in an image, which is the rust. So we have built that and built a custom dataset, which is to be fed to the mass RCNN model. And here is our process flow for our study, which aims to develop a rust detection system that can classify rust based on visibility and locate rust on the classified images. A PyQt5 graphical user interface or GUI was developed that can capture images from a camera. This GUI holds the CNN model and can execute the classification process. Then the classified images are saved to a local directory. An execute button can be used to upload the classified images to Google Drive. A Raspberry Pi 4 uh, is used to hold the mass RCNN model, and a Python script can be used to download the classified images from the Google Drive. Then the same script automatically locates the rust in the classified rust images. So for the evaluation, the confusion matrix was used to evaluate CNN in rust classification by using the test set and feeding it against the trained rust classification model. On the other hand, the average precision or AP metric was used to evaluate mass RCNN in rust localization by using the same test set and feeding it against the trained rust localization model. Now to test the prototype's performance under different light intensities, sample rust images belonging to each rust category were subjected to the prototype's rust classification and localization. The light intensities are 160,000 lux, 5,000 lux, and 10 lux. The prototype's performance in rust classification under different light intensities was evaluated by calculating the accuracy of the rust classification prediction under these different light intensities. 5 trials were conducted and the average accuracy was calculated. On the other hand, the prototype's performance in rust localization under different light intensities was also evaluated by getting the standard deviation of the number of instances under these 5 trials. So for the results of the rust classification, the confusion matrix shows that CNN had an overall accuracy of 0.8 point 0.8 or 80% on the test set. On the other hand, the average precision or AP was used to measure the performance of the mass RCNN. The metric value known as AP considers the precision recorded curve, intersection over union or IOU, confusion matrix, and other object detection measures. And results show that mass RCNN obtained an AP50 value on its box parameter with a value of 70.958 and its segment parameter with 70.139. The results show that an IOU or intersection over union threshold of 50%, ROS can be located by the mass RCNN model with significant performance. We have also compared this to a previous study, and it shows that the results for CNN has a better classification, while mass RCNN performs sufficiently for localization. And here it shows the accuracy of how many times did the Rust classifier correctly predict the classification of the trial images under different light intensities under 5 trials. A value of 1 tells that the Rust classifier correctly predicted the trial images to its actual known classification 5 times out of 5. And it can be observed that the classification result for each Rust category is better and more consistent when the light intensity reaches 160,000 lux. Here it shows how consistent the Rust locator or the mass RCNN model is under different light intensities under 5 trials. The standard deviation of the number of instances recorded under the trials for each class was used to determine the consistency, and it is observed that the localization performance under different light intensities was more consistent under 160,000 lux. So advantages and disadvantages of the prototype. Advantages is that the system can classify images up to 640 by 640 pixels. It can classify images without the need to convert it into grayscale. The user can immediately identify where the rust is as the system can locate and highlight the rusty areas and spots in an image. And lastly, the system can quickly classify and locate rust in each image, allowing the user to obtain the results instantly or potentially input larger batches of images for classification and localization. Disadvantage is that it can only classify and locate rust on its surface, and the method is dataset reliant. So in conclusion, CNN obtained an accuracy of 80% on the test set, and mass RCNN obtained an AP50 value of 70.958% on its box parameter and an AP50 value of 70.139% on its segment parameter, which shows good performance. And classification and localization performed better and were more consistent when the lighting environment reaches 160,000 light intensity. And this shows that the method used in the study was successful in detecting rust. So here is a prototype demo. As seen here, images of rusted galvanized iron sheets are being captured. One that is clear sheet and one that is a rusted sheet. And here is the capturing of the GUI and the execution of the classification model. As seen here, here we are uploading the classified images to the Google Drive. And now in the Raspberry Pi, we are downloading the classified images from the Google Drive to the Raspberry Pi. And now here it is now downloading and executing the Rust localization model on the downloaded classified images. and here's the output. And that is all. Thank you.